Hello everyone, welcome to our new and exciting learning platform Catalyst for IIT JEE. Myself Subendu from IIT Kanpur, and this is the second lecture of our basic lecture series on the gaseous states of matter. So these are the things which we want to cover in our basic lecture series. In the first lecture we talked about the different states of matter with their characteristics. From today's lecture onward, we will specifically talk about the gaseous state of matter. So the gaseous state of matter is the main focus of our lecture series. In today's lecture, first we will discuss about the gaseous state and their kinetic theory. We will also talk about the molecular speeds and kinetic energy of gas molecules. So now let's talk about the gaseous state of matter. So if you remember our first lecture, then you should know that gases have no definite shape and volume. You also know that the gas can flow easily to any direction. So these two properties of gases we have learned from the first lecture. Now there are some other properties of gases as well which are very important. First one is the volume of a gas is equal to the volume of the container. Second, the density of gases is much lower compared to solids and liquid. Third, gases exert equal pressure in all directions of the container. Also, the gases are highly compressible. Compressible means the volume of a gas can be decreased much more easily compared to solids and liquids. So the gases are highly compressible compared to solids and liquids. Now the question is, can we explain this behavior of gases in terms of their molecular details? The answer is yes. Kinetic theory actually do this task. So kinetic theory basically explains the physical properties of gases in terms of their molecular description. Now what is kinetic theory? So kinetics is related to the motion, and theory is a proposed model for better understanding. So kinetic theory is basically a model regarding the motion of the gas molecules so that we can understand the behavior of gas very clearly. But before explaining something from a theory, first we should learn about the postulates. Now what are those postulates? Postulates are the assumptions or the starting points, you can say, that we should accept as the pillars of the theory. So in order to explain something from a theory, first we should learn the postulates of the theory. So what we will basically do now, we will discuss about the postulates of kinetic theory one by one, and we will also explain the properties we have just discussed in terms of these postulates. So let's come to the first postulate of the kinetic theory. The first postulate tells that a gas is a collection of small and identical particles known as gas molecules. The distances between the molecules are very large compared to solids or liquids. So this picture actually represents the gaseous system, and the system is composed of these small blue balls. So these blue balls are basically the gas molecules. So as the distances between these balls or these molecules are large, there will be lots of empty or free space available between the molecules. The empty space is the space not occupied by the molecules. So as there are lots of empty space available between the gas molecules, now if we try to decrease the volume, then what the molecule will do, the molecules start to come closer, and as the molecules start to come closer, the void space is decreased in size. That is why decreasing the volume becomes very easy for the gases. On the other hand, for solids and liquids, molecules are already closer to each other. So the void space for solids and liquids will be very small. Now if we try to decrease the volume, of solids and liquids, the decreasing volume will not be so easy. So, at this point we are able to understand the fact that why gases are highly compressible whereas solids and liquids are not. So, the first postulate of the kinetic theory helps us to understand this fact. Now, let us discuss another important property of gas from the postulate we have just discussed. So, now we are going to explain the low density of gas in terms of the postulate. So, let us consider these three pictures which are shown here. So, in these three pictures, three blue balls are taken in this volume. So, the volume is basically the same for these three pictures. Now, if we move from left side to right side, we can see that the distance between these molecules or these balls are increasing. Now, as the distances between these balls are increasing, the number of molecules in this volume is decreasing. So, for this picture, the number of molecules in this volume is 3, and for this picture the number of molecules in this volume is 1. So, number of molecules per unit volume, if we think this volume as unit volume, so number of molecules per unit volume decreases if the distance between the molecules increases. Now, density is equal to mass divided by volume or mass per unit volume. Now, we all know that mass will be proportional to the number of molecules. So, if we increase the number of blue balls here from 3 to 4, then the mass occupied in this volume will be increased. So, more the number of molecules, more will be the mass in this unit volume. So, the density, which is the mass per this unit volume, is proportional to the number of molecules per unit volume. Now, as the distance between the molecules is very large for the gases, so the number of molecules per unit volume will be very low for the gas molecules or for the gases. So, the number of molecules per unit volume will be decreased as we move from solid to liquid to gas, and as the density is proportional to the number of molecules per unit volume, so the density will be decreased as we go from solid to liquid to gas. So, for the solid the density is highest and for the gas the density is lowest. So, now we can also understand that how the postulates of kinetic theory helps us to explain the density of the gas. Now, in our first lecture we discussed that for a gas the intermolecular attraction is very negligible. So, the kinetic theory basically assumes this negligible amount of attraction force as 0. So, here comes the second postulate of kinetic theory. So, second postulate tells that there is no force of attraction between the gas molecules. So, what we can interpret from this postulate is that if the molecules would attract each other, they would remain closer to each other by the attraction. But as there is no force of attraction between the molecules, they always remain as far as possible. Now, if we want to keep these molecules in a container, then the molecules expand and occupy the whole available space or the whole available volume of the container. So, now we can understand the fact that why the volume of a gas is equal to the volume of a container. Now, from the first lecture we also learned that due to the thermal motion the gas molecules move randomly. So, that is nothing but the postulate 3 or third postulate of the kinetic theory. So, third postulate basically tells that in a gas, molecules always move freely to any random direction along straight line. So this is the picture or the molecular details of a gas. So as you can see here that all the molecules are moving to any random direction. So this random and constant movement of the molecules are called Brownian motion. So this Brownian motion can be seen for the gas molecules, and this is a very important phenomena for the gas molecules. Now due to this motion, the position of molecules are changing very frequently. So if we take snapshots at two random time, we will get different arrangement of molecules. So basically the arrangement of gas molecules change very rapidly due to their thermal motion. That's why the gases have no particular shape, their shape always change. On the other hand, for solids, the molecules are at rest. From the first lecture we are familiar with this fact. For solids, as there are strong intermolecular force of attraction, the molecules are at rest, and as the molecules are at rest, the shape of the solids is fixed. So from this postulate now we can understand why the gases have no shape whereas the solids have some definite shape. Now let us come to the fourth postulate of kinetic theory. So according to the third postulate, the molecules in a gas undergo a random and free Brownian motion. Now during this Brownian motion, if any two molecules or any molecules come to a particular position, then they collide. So during the Brownian motion, molecules continuously collide with themselves. Also they can collide with the wall of the container. Now during the collision with the wall, when the molecules get bounced back from the wall, a change in momentum can happen, and according to the Newton's second law, the change in momentum results a force on the wall. So this force divided by the area is actually the pressure of the gas. So the pressure of the gas is due to the force exerted by the molecules on the wall during the collision. Now as the motions of the gas molecules are free and random in all direction, so the molecules can bounce back from the wall in all direction exerting equal force. Consequently, the pressure of the gas becomes equal in all direction because the area don't change for a fixed container. So now we can understand that why the gases exert equal pressure in all direction. Now let us come to the fifth postulate of the kinetic theory. Fifth postulate tells that the collision between the gas molecules are elastic. So now the question is, what are these elastic collisions? An elastic collision is a collision where individual energy of colliding particle can be changed, but the total energy of the colliding particle remains same before and after the collision. Now let us assume that before collision the energy of the molecule 1 is E1 and the molecule 2 is E2. So the total energy will be E1 plus E2, right? So before the collision the total energy is equal to E1 plus E2. Now as our fifth postulate say that the collision between the gas molecules are elastic, so according to the postulate the total energy will be equal to E1 plus E2 after the collision. So after the collision the individual energy which are E1 and E2 can change, but the total energy, that is E1 plus E2, will be fixed. So now it is our time to discuss our last or sixth postulate of kinetic theory. According to this postulate, due to the continuous collisions between the gas molecules, the individual speed of all the molecules cannot be the same at any particular instance. Suppose all the molecule in this container starts from the same speed. So as the molecules here have same speed, they are represented by the same color. Now if we let this system to go for some time, and if we take a snapshot at any random time, then we can see the picture like this. So in this picture, the speeds of all the molecules are not same. Instead, different groups of molecules have different speed, and these different groups are actually represented by different colors. So for this picture, the different groups of molecules having different speed are actually represented by green, pink, violet and blue color. So among these two pictures or two different cases, the first one or the picture in the left side is not possible, because the continuous collision between the gas molecules makes the difference in the speed of the gas molecules. So this is the actual case of the gas molecules. So what we can summarize from the last postulate is that in a gas all molecules do not move in the same speed. Instead, different groups of molecules possess different values of speed. So this is actually called the distribution of speed. So as the individual speeds of all the molecules in a gas are not same, so we cannot express the absolute speed of the molecules. Instead, we express their speed in different ways. The first way to express their speed is the average or mean speed. So how we calculate the average speed? Average speed is equal to the summation of speed of all the molecules present in the system divided by the total number of molecules. Now consider that in a gaseous system or in a gas there are n molecules. Now if we make a list of individual speeds of all of these n molecules, and if the list looks like this, where C1 is the speed of first molecule, C2 is the speed of second molecule and so on. So to determine the average speed or to get the average speed, we have to add all the values from C1 to Cn, and then we have to divide this summation by the total number of molecule present in the system, that is capital N. So in general, the average speed, which is expressed here as C average, can be written like this. Please remember, this symbol is nothing but the symbol used for summation. So here the summation is taken from 1 to n, as there are n molecules present in the system. So the CIs are nothing but the individual speeds of molecules. Now let's come to the second way of expressing the speeds. This is root mean square speed or RMS speed. So root mean square speed is the square root of mean square speed, and mean square speed is the average or mean of square of speeds. So if we take the summation of square of speed of all the molecules, and if we divide this summation by total number of molecules, then we will get the mean square speed. So for the same list we have made just before, the mean square speed, which is expressed as c square bar here, so this c square bar can be written like this way. So for the list of this speed of n molecules, the mean square speed is the c1 square plus c2 square plus c3 square up to cn square divided by capital N. Now for mean square speed, if we want to calculate the root mean square speed, then we have to just take the square root of this c square bar. So basically the root mean square speed, which can be expressed as c RMS, is the square root of c square bar, and c square bar is equal to this. So finally this is the expression for the root mean square speed. Now let's come to the third type of expressing the speed, that is most probable speed. So the most probable speed is basically the speed possessed by the maximum number of gas molecules. So let's look into this picture here again, where the different groups of molecules having different speeds are represented by different colors. So here these molecules form 4 different groups according to their speeds, and these groups are represented by the pink, blue, green and purple color. Now if we consider that these 5 pink molecules present here move with C1 speed, 7 blue molecules move with C2 speed, 6 green molecules move with C3 speed, and 4 purple molecules which are present here move with C4 speed, then we can easily say that 7 is the highest number among 5, 7, 6 and 4. So the most probable speed will be the speed possessed by the 7 blue molecules, because 7 is the maximum number of molecules having same speed. So the most probable speed will be equal to C2, because C2 is the speed possessed by 7 blue molecules, and these 7 molecules is the maximum number of gas molecules having same speed. Okay, so now let's think about a problem. Consider a gas composed of 6 molecules. Among them, if 3 molecules have a speed of 10 meter per second, 2 molecules have a speed of 20 meter per second and 1 molecule has a speed of 30 meter per second, then calculate the average, RMS and most probable speed. So here meter per second is the unit of speed. So please do the calculation by yourself and write the answer in the comment section. In the next lecture, we will upload the step-by-step explanation for this answer. Now, the information that was given for calculating the answer is nothing but the number of molecule at each different value of speed. So, to determine the average, RMS and most probable speed, we need to determine how many molecules are there in a particular value of speed, because without this information it is not possible to calculate the average, RMS and most probable speed. Now the question is, in reality, is it possible to determine the number of gas molecules at each value of speed? Yes, it is possible. Two famous scientists named Maxwell and Boltzmann derived the formula which is known as Maxwell-Boltzmann formula for calculating the number of molecules at each different value of speed. Now let us look into this graph here, where the x-axis actually represent the value of speed and the y-axis represent the number of molecules. Let us assume that for a particular value of speed, that is Ci, the number of molecules from the Maxwell-Boltzmann formula is Ni. So the coordinate of this point in this graph will be the value of x-axis, comma the value of y-axis. Here the value of x-axis is Ci and the value of y-axis is Ni. That means the coordinate of this point will be Ci, comma Ni. Now if we do the same job for all the possible values of Ci, we get a collection of these points. Now if we connect these points, we will get a curve. This curve is nothing but the Maxwell-Boltzmann distribution curve. This Maxwell-Boltzmann distribution curve is very important characteristics for the gas molecules, and we will discuss about this curve in more detail when we will discuss about the Maxwell-Boltzmann distribution formula in the advanced lecture series. As I said before, that to determine the average RMS and most probable speed for a gas, what we need is the number of molecule at different values of speed. We also know that from Maxwell-Boltzmann formula we can determine this number of molecules. So, from Maxwell-Boltzmann formula the mathematical expressions for different speed can be derived, which are shown here. So, average speed or C average is equal to root over of 8RT by pi m. RMS speed or C RMS is equal to root over of 3RT by m, and most probable speed or CMP is equal to root over of 2RT by m. Here R is a constant known as universal gas constant, T is the temperature of the gas in Kelvin, and m is the molecular weight of the gas. Please remember that here the speed of a gas is dependent upon the temperature, which is capital T, and the molecular weight, which is capital M. Remember, R and pi are the constant here. So, the speeds only depend upon T and M. Now, for a particular gas, if we take the ratio of these three different speed, we will get this number. So, for a particular gas, the ratio of most probable, average and RMS is equal to 1 is to 1.128 is to 1.224. That means, if the value of most probable speed is 1, then the value of average speed will be 1.128 and the value of RMS speed will be 1.224. From this we can interpret that for a particular gas, most probable speed is the lowest, average speed is greater than the most probable speed but lower than the RMS speed, and RMS speed is the highest. Now, let us consider again the Maxwell-Boltzmann distribution curve. Now, when we are at the peak or at the maximum of this curve, the value of y axis is maximum. So, the length of this line is actually the value of y axis, and here y axis actually represents the number of molecules. That means, at the peak point number of molecules are maximum. Now, the value of x axis or the value of speed at this peak is actually corresponding to the speed possessed by the maximum number of molecules, and the speed possessed by the maximum number of molecules is the most probable speed, right. So, the most probable speed is the speed at the peak or maximum of the Maxwell-Boltzmann distribution curve. Now, for a particular gas, the three different speeds, the order of the three different speeds looks like this. Now, as we move along x axis from left to right, the value of speed gets larger. So, as the average speed has a greater value than the most probable speed, then the average speed will sit at the right side of the most probable speed. So, this will be the position of average speed. Similarly, as the RMS speed has a greater value than average speed, so the RMS speed will sit at the right side of the C average. So, this will be the positions of three different speed at the Maxwell distribution curve. So, from left to right, most probable speed, average speed and RMS speed will be there. Now, let us talk about the kinetic energy. So, kinetics is related to the motion. So, the kinetic energy basically mean the energy of something in its motion. So, when a gas molecule moves, it has some kinetic energy. Now, mathematically we can write the kinetic energy as half into mass into speed square. Now, during the collisions, as the speed change, the kinetic energy will also be changed due to the collision, because the kinetic energy is dependent upon the speed. Now, for a moving particle of mass m and speed c, we can write the kinetic energy E as half into m into c square. Now, like the speed, the kinetic energy also change due to the collision. So, we cannot measure the absolute value of kinetic energy. Instead, we can measure the average kinetic energy. Now, from this equation, if we take the average, we can get that E average or E bar will be equal to half into m into c square bar. Now, we know that C RMS or RMS speed is nothing but the square root of c square bar. So, c square bar is equal to the square of the RMS speed. That means the average kinetic energy will be half into m into c RMS square. So, in today's lecture, first we have discussed the postulates of kinetic theory of gas, and we have also explained the physical behavior of gas in terms of the kinetic theory. Then we have discussed about different types of speed, which are average, RMS and most probable speed. Last, we have discussed about the kinetic energy and average kinetic energy of the gas molecules. So, thank you for being there with me in this lecture. Our next lecture, that is lecture 3, will be coming soon. If you think that this video is helpful for the students, then don't hesitate to like and share as much as possible. Also, don't forget to subscribe our channel by clicking the bell icon. Thank you so much.